2.1 talks about rates of change and limits. Limits are the foundation of everything about calculus. The definition of derivatives and integrals are both found with limits, so we need to make sure we really have a good grasp of what a limit is. So let's start with an average rate of change. You know that you have a formula, distance equals rate times time, and that this is the average speed over that time period. It's the average rate. The way we figure it is the change in the distance divided by the change in the time. Remember, this is a delta and it means the change in. So we find our average rate. But what happens if we want to know what our instantaneous speed is at a particular time? When we have an instantaneous speed, we can't look at the delta because our delta at that instance for an instantaneous rate of time would be 0. So if we're looking for an instantaneous speed, our delta t is 0. You can't divide by 0. We end up with an undefined term. So what we have to do is we find what happens as our delta t goes towards 0. This is a limit. If you look in your book on page 55, it gives you a couple of examples with this. The first example talks about that average speed, this here, and it talks about how you find that. And then the second example talks about instantaneous. So let's look at that one. If you have a rock that breaks loose from the top of a tall cliff, and you want to know what the instantaneous speed is at time t equals 2, so we have this rock that's falling, and we want to know what its speed is right here at times t equals 2 seconds. So the way we want to figure that is, if we figure out what our change in y over our change in t is, well, the change in y, up in example 1, it tells you that y is 16t squared. This is a physics equation, so we're not going to go into how to derive that. But if we want to know what the instantaneous speed is right there, we need to figure out what our t is for our time. So what we're going to do is we're going to figure out what happens at time 2 from time t equals 2 seconds to time t equals 2 plus h. And h is just going to be this really small amount so that we can figure out right up close to the t equals 2. Because if we have time t equals 2 for both the start and the finish, then we end up with 0, which will mess us all up. So what we're going to do is calculate this average time in this very small amount of time. So our average rate of change, is 16 times, and then we take the later time, 2 plus h squared, minus 16 times the earlier time squared over the later time minus the earlier time. So we're finding an average rate of change, but we're finding it in this really, really small time. And when you what you end up with, if you simplify this all down, you get 64h plus 16h squared all over h, and then you can see you can factor out an h, and you end up with 64 plus 16h. Now what this means is if our h is 0, so that we're at this instantaneous time, then our instantaneous rate of change is 64 meters per second. So what we're doing is we're looking at these really tiny little small intervals and bringing them down to being just 1 point. So let's get an official definition and see if we can work with this. Now, I'll warn you, the official definition is long and mathy, and I'm going to give it to you, but we're not really going to use it that much. It's kind of for higher level stuff to use the specific limit definition. So, what's a limit? Let C and L, so we need some numbers here, be real numbers. The function f has a limit L as x approaches C if given any positive number epsilon, there is a positive number delta such that for all x, this equation is true. Now, what in the world does that mean? Well, what that means is, if you have this function and you have this value c, there's, for an x value, let's make it a little bit easier to see here. So if we started this x value, some x value, then this space between the two is delta. And there's a function value here that goes with the c. And, there's a function value that goes with the c that we're going to call L. And as our x value gets, this space is called epsilon, so as our x value gets closer and closer to c, our function value is going to get closer and closer to L, and these spaces are going to get smaller. Okay? All we're doing is seeing what happens as we get closer and closer and closer to this value here for x. What does that do to our function value? Now, the way you write this is the limit as x goes to c of f of x equals L. Okay, this is what you need to be most familiar with. As we do some examples, it'll make some more sense. Now, one thing you need to realize, this function does not have to be defined there. You could have a big old hole or an asymptote or anything. The function doesn't have to be defined there for the limit to exist, because it's still going towards that value. It's still getting close to there for you to have a limit. The limit is what it's getting close to. It's approaching, not what it's necessarily defined as at that place. All right, so let's look at some examples here. All right, if we want the limit as x goes to 2 of x squared plus 3. Now, this is a polynomial, so it's defined everywhere. So we can just plug in our value and we'll get what the limit is. Because what we want is, if this is x equals 2, right here, see in the second little dot here, then we want to know what's the function doing as we get closer and closer to 2 from both sides. Well, this function is smooth and continuous all through here, and defined there, it's all the same thing. So all we have to do is plug in 2 to get the value. If you plug in x equals 2 here, you get 2 squared plus 3 equals 7. So if we look at our graph, what that means is, if we calculate the value at x equals 2, we get 7, and that's our limit. If the function's defined there and it's a smooth continuous curve there, then it's easy. You just plug in the number and the value there is what it's going to. Now if it's not that, then it'll be a little more complicated, and we'll use the tables. The way you use your tables on your calculators, you hit second graph, and that's the table. And it'll show you values if you have different x values, what does the y value come out to be? And you can see that if you arrow up to the 2, you get your y value of 7. Now sometimes this works perfectly, and what it is what it is. It gets right there because it's a smooth continuous curve. But we're going to look at some examples where it doesn't always work like that, because most of the time limits aren't quite this simple. So let's look at another one. Let's say we have the limit as x goes to 1 of x squared minus 1 over x minus 1. Now, if you look at this one, you see that if we plug in 1, we're going to get something undefined. So we can't just plug in 1 for this. So let's look at the graph. If you plug it in and graph it, you see that it looks like a line, and it actually looks like it's smooth and continuous there. But if we look at our table, hit second graph and go to the tables, if we're going to see what happens at x equals 1, and you can change your table settings so that it is right around there if you want. So you don't have to arrow through everything to get to what you want to. The table settings are above the window button. So when we get here, alright, so let's look at this x equals 1. So as we're getting closer and closer to x equals 1, our y value is getting closer and closer to 2. And here we're getting closer and closer to 1, and again our y value is getting closer and closer to 2. That means that the limit is 2. So if the limit is 2, we can look at our graph again, and you can see that as you go along here, x equals 1, you're getting closer and closer to 2. But it's not defined there. Now, how does that help? How can we figure that out when we're not looking at the graph? Because you're not always going to be able to do limits with the graph. Well, we can simplify it algebraically and it'll show us. If you take the function x squared minus 1 over x minus 1 and simplify that, we factor. And if you'll recall, when we talked about rational functions, we said if we had a rational function where something canceled out, what that meant was we had a hole there. So this function here looks like this line with the hole at x equals 1. And my window is all, that's what I thought. My window is pretty weird, so we're going to change it. I changed my window to a standard window so you could see it better. So when you have a rational function, the first thing you want to do is see if you can simplify it, because this takes out our hole, and now we can plug in x equals 1. We plug in x equals 1, and we get 2. So this is how you would solve it algebraically. And on the graph, you just use the table. Now, on page 58 in your book, there are a whole bunch of properties that you need to look over and read over and make sure you know. The multiplication by a constant, there's sum and difference, product rules, quotient rules, power rules, all those things you need to know, because limits, it's a different way of doing things. It's kind of like adding and subtracting and multiplying and dividing. It's something you're doing to these functions. So you need to make sure you understand how you can manipulate them. For example, with this one, let's say we change this up and we say the limit as x goes to 1 of 3 times this. Well, if we look over in our book to rule number 4, the constant multiple rule, we see that we can have this constant here, and it is going to come out front. It's going to be 3 times the limit of just the function. Well, we know what this is. This is just 2. We already calculated that. So the limit of 3 times that function is the same thing as 3 times the limit, which means it's just 6. So let's try another one. What if we have the limit as x goes to -1 of x squared minus 3 to the 10th power? Well, we can use that power rule number 6. And what this means is the limit as x goes to -infinity of x squared minus 3 to the 10th. So if we have the limit of a function to a power, then we can just take the limit of the function and raise it to the power. Well, here we have a polynomial. It's defined everywhere. So we can easily plug that in. -1 squared is 1, minus 3 is -2. So our answer is going to be -2 to the 10th power, which is just 1024. So that's a power rule. Now, there's a bunch of those rules on that page. Make sure you read over this. It's very important you read every section. So read over those especially. You may want to put them on your note cards for your studying the definition of a limit and these properties of a limit. Now, the other thing that we need to look at is on page 59, the polynomials. We've already seen that we can just plug things in for the polynomials, but this theorem just states it explicitly. If you have the limit as x goes to some number c of a polynomial, then it's just going to be fill it in. This is what we just did. Now for a rational function, you can also do this because remember, a rational function, you have polynomials on the top and the bottom a lot of the time. If it's a rational function with polynomials on the top or the bottom, then you can also just plug it in as long as that's not equal to 0. So if we have a polynomial divided by a polynomial, these are smooth and continuous and defined everywhere, so we can just plug in our value and we have the limit because it goes right there. Sometimes we can look at limits and we don't want both sides. Sometimes we look at a function and we want to see, like say we have a function like this, and we want to know the limit here at this x equals c, but it's different. We can come in from the right or we can come in from the left. We're going to get different values. So we have one-sided limits. So the limit as x goes to c from the left is how we write this. So that little minus sign means from the left. Or we can do the limit as x goes to c from the right of the function. Now, for the limit to exist, then you have to have the condition where the limit from the left is equal to the limit from the right. Now you can look at this particular function here and see from the right we're going to get way down here, and from the left we're going to get way up here. Those are not going to be equal, which means that the limit as x approaches c of this function does not exist. Now let's look at a special case here. This is a limit that you are going to have to make sure that you know. So put it in your calculator. And I'm going to zoom trig it so that it looks right. And we're going to calculate. We're going to freak out again. Sorry, you know how this calculator thing goes. Sometimes it works and sometimes not so much. There we go. All right. So this is the graph. Now, obviously, if we have x equals 0 and we're dividing by 0, it's not defined there, so we're going to use our table. And we're going to go down to x equals 0. Like I said, you can change your table settings every time if you want to be able to get, and it's freaking out again. Sorry. Okay. So it's kind of hard to see that, but not sure why it's not zooming in. But anyway, you can see that it makes an error at x equals 0, obviously. But as we get closer and closer, we're getting to 1. You need to know this limit. It will come up a lot. You need to know that the limit as x goes to 0 of sine x over x equals 1 every time. We're not going to prove it. We're just going to, I'm just showing you on this table here for the graph, but this is something that you need to have memorized. Now let's look at a couple of examples here quickly. Let's look at the limit as x goes to 0 of the square root of x. Well, if we look at the graph of the square root of x, we see that if we come in from the left, then it doesn't exist. And you just write DNE, does not exist. And if we come in from the right, it's equal to 0. So we come in from the right, it's equal to 0. We come in from the left, it doesn't exist because there's nothing there. Which means that this limit does not exist. Another function that you really need to know is the greatest integer function. It's often written this way. Sometimes, especially in your book, it's written INTX. Remember, that's the stair step one, where you do the step like this. So if we're at x equals 2, then the limit as x goes to 2 from the left of the greatest integer function is 1, but the limit as x goes to 2 from the right of the greatest integer function is 2. So this limit does not exist. So Make sure you're paying attention to this one. Make sure you know what the greatest integer function is. Now we're going to run through very quickly, because we're almost out of time here, the sandwich theorem. This is really important. We'll talk about it some more in class. But the sandwich theorem says if you have a function, g of x, and it's smaller than your f of x, and then you have another function, h of x, that's even bigger, then for every x not equal to the c in some interval about c, so you're right near it, and you know what the limit is as x goes to c of g of x, and you know what the limit is as x goes to c of h of x. You know they're both equal to each other and it's L. Then you know that the limit, sorry, I'm trying to hurry here and I'm getting off track. The limit as x goes to c of the f of x equals L. Now what does this mean? Well, if we have this function h of x, and we have this other function g of x, and then we have this weird function f of x, if this is our c here, then as we're going, we find the limit for h and we find the limit for g. Because f is between these two functions for some interval around c, then that limit's going to be the same. Let me see if I've got time for one quick example here. The limit as x goes to 0 of x squared sine x. Well, we know that sine x is always between -1 and 1. So that means that x squared sine x is always between -x squared and +x squared. Think about that for a second. Make sure you've got that. So if we know that the limit as x goes to 0 of -x squared is 0, and we know that the limit as x goes to 0 of +x squared is 0, then that means this limit is 0 as well. We'll talk about that some more in class to make sure you've got it. Make sure you've read through that section, write down any questions you have, and we'll go over this some more in class.